Okay, we are going to talk about the section 4 prerequisite section. This is about inverse functions. Inverse functions basically are functions that undo other functions. So in other words, if we have a function that has x in the domain and f takes x to f of x in the range, the inverse function will take any element of f of x back to that original element in the domain, and the notation is f with like a -1 exponent. Different than to negative first exponent, which causes us some confusion sometimes when we talk about the trig functions, and I'll talk about that later in this video. Okay, so we would say that g is the inverse function of f when if we take g of x and plug it into f of x, we get back to x for all x in the domain of g. And if we plug f into g and it takes us back to x for all x in the domain of f. So in other words, if you start with x, it goes back to x when we apply the two functions. Okay, so the notation there is we would say g of x is equal the inverse of f, and that's the notation that we use. Okay, so we can use the definition here, and I will tell you that a lot of times the focus in earlier classes are finding functions, but not really looking at the definition. This definition is very important to us, and sometimes they won't even tell you f and g are inverse functions, but they'll give you this information. And as soon as you see that you're getting back to x, you know that that's an inverse function. So let's say we have f of x equals x to the third plus 1, and g of x is equal to the cube root of the quantity x minus 1. We want to show those are inverse functions. Okay? So the way we do this is we start off by plugging g into f. So wherever I see an x and f, I'm going to plug in g. And you can see quite simply, and there's not a lot to do here, if I raise a cube root to the third power, those are going to be undone. That is then going to leave me with x minus 1 plus 1, so that gives us x. So that's half of it done, right? So that's showing that if we plug g into f, we're getting back to that value x, which is what was plugged into the original domain. And then we're going to do the same thing, but in reverse. Okay, so if we take f and plug it into g this time, oh, that's minus 1. And then once again, we can quickly see what's happening here. We're going to get x to the third plus 1 minus 1, so that leaves us x to the third. Then we're going to take the cube root of x to the third, and that gives us x. So then we know that g of x is equal to the inverse of f. All right? So that is conceptually the definition. All right, now we're going to look at this in a couple different ways. Okay, the next way we're going to look at inverse functions is graphically. So graphically, what happens is, let's just take, a lot of times when I'm doing these functions, I look at x to the third. So let's just think of x to the third. I'm going to use this a couple times for an example. We know we get a function that looks something like this. Okay, x to the third is the inverse function as a cube root of x, which we did a similar one last time. How we look at it graphically, and it doesn't have to have an algebraic part of it, is that if we take the line y equals x, which is that diagonal line there. Oh, that's supposed to be a straight line. So if we take y equals x, so let's call this f. F inverse will be reflected over y equals x. Okay? So what we want to do, and you know, if you're good at this, great. This point will be the same, this point will be the same. So the points that are actually on y equals x will be the same. And what happens is we're going to reflect over. So I'm going to try to make this look like it's a reflection. Oops. Okay, not bad. So that would be our inverse function. If you do get confused, you can look at the values and just flip the x and y, and that's what's happening graphically. So what does that mean if we're looking at this thing numerically? So numerically, or using a table, which, you know, let's just take a function numerically. And by the way, when you're given a numerical function in a table, you can't assume, even if it sort of matches up with some algebra, you know, you can't assume that algebra unless they specifically say that it does match up with that particular algebra. I'm choosing one that's quite random, and you would have a hard time coming up with an algebraic formula for that. So let's say we have 0 goes to 7, 1 goes to 13, 2 goes to -4, and 3 goes to 2. And let's say our function is just that function that does that. Takes those 4 elements here to those 4 elements here. What would that inverse look like? Well, simply, you're just flipping the x and y, okay? So -4 goes to 2, okay? 2 goes to 3. 7 goes to 0. And 13 goes to 1, right? So we're getting that relationship we talked about in the first thing. If we think about 0 to 7, and if we plug in 7, we're back to 0. So it's doing what we see in the definition. It's taking our original value and bringing it back to us. The inverse function is undoing that. Okay. Before we get into the algebraic, we do have to talk about whether or not a function has an inverse function. Okay. So if we're talking about the existence of an inverse function, what we're talking about is a quality that has a specific name. It's called one-to-one. You know, we often forget what this is. Whether you sort of recall it's one-to-one or not doesn't really matter, and I'll talk about this in a second. What one-to-one means is a function or let me rephrase this. Each input of a function has a unique or an unique output. So outputs cannot be duplicated. Okay? So what that means is, once again, let's go back to our x to the third. So let's go y equals x to the third. Okay. That is one-to-one. So this is one-to-one. So this is one-to-one, x to the third, because we don't repeat any outputs. Okay? Y equals x squared is not one-to-one. And the reason why is, if we look over here, we're repeating an output. So graphically, numerically, what we're talking about is, if you look at x to the third versus x squared, let's just take a look at a few values here. -2, -1, 0, 1, 2, right? We get -8, -1, 0, 1, and 8. All those outputs are unique. And there's an infinite number of values, but all of those outputs are unique. Now, with x squared, of course, we get repeats of the outputs. So this gives us 4, this gives us 1, this gives us 0, but then we get 1 again, and we get 4 again. So we see, because those are repeated, this is not one-to-one. So before we can have a discussion about whether or not we have an inverse function, or whether we're going to find an inverse function, we have to take a look at whether it's one-to-one. Okay? Now, graphically, what that means, and you can think about this, is we know that functions have to pass a vertical line test in order to be functions. Okay? So graphically, in order for a function to be to have an inverse, or to be one to one, it has to pass a horizontal line test. Okay, and it's easy to see why, right? So if I think of x squared, if I want to do the inverse function, so once again, let's look at this graphically, right? So I'm going to reflect it over the line y equals x. Okay, so what's going to happen here is I get something that looks like this. So what happens is our inverse, which is not ends up not being a function because it doesn't pass the vertical line test. Okay, so we all know functions have to pass vertical line tests. In order for their inverses to also be a function, they have to also pass a horizontal line test, and that's what's called one-to-one. Okay? Now, we'll get into this a little bit later, but if we do have a situation where a function is not one-to-one, but we still want to talk about an inverse function, what we end up doing is limiting the domain. So for instance, we could talk about the inverse function of x squared. For instance, if we just said, we're going to limit our discussion to x is greater than or equal to 0. So now we've limited the domain, and now we can talk about an inverse function. This becomes very important when we start talking with the trig functions and the inverse functions, which I'll get to in a moment. Okay, so next, let's take a look at this algebraically. Okay, so if we're looking at this algebraically and we want to find an inverse function, this tends to be something that you've seen before, and a lot of times you focus on the algebraic. So for instance, if I give you the function f of x equals 2 times the cube root of x plus 7, and I ask you to find the inverse function, it's pretty easy algebraic manipulation. So what you do essentially is, the f of x, we're going to plug in x. Everywhere we see an x, we'll plug in a y. And ultimately, all you have to do is undo everything to get at that y. Once you get that y, that's your inverse function. So for instance, here I'm going to start by dividing both sides by 2. Okay, now I want to undo the cube root. The way I undo a cube root is I raise it to the third power. So I'm going to raise both sides to the third power. So here, top gets raised to the third power, bottom gets raised to the third power. So this would be x to the third over 8. And now we're just left with the plus 7. So the last thing I have to do is subtract 7 from both sides. So I get x to the third over 8. Let's just call that 1/8. Minus 7 is equal to y. So now I have it. So my inverse function for f is 1/8 x to the third minus 7. So those tend to be pretty easy. Let's do one that sometimes people have difficulty with. If I gave you a function f of x is equal to x over x plus 3, sometimes people have issues with the rational functions. So in this particular case, once again, well, all of them, I switch the x and y. Okay, now I got to solve for y. Now as soon as I see this fraction, I'm thinking, you know what, it would be better off if this wasn't a fraction. So what I'm going to do is I'm going to multiply both sides by that quantity in the denominator. So the y plus 3, I'll multiply to both sides. So this is going to cancel. I'm left with y over here. And now, let's distribute the x, so I get xy plus 3. Now I have to solve for y. So in this particular case, you know, we see this as, actually that's 3x. There's two y's. Well, what do we do when there's 2? Well, it's pretty simple once you realize what the procedure here. We're going to get anything that has the thing we're trying to solve for on one side. Any term that doesn't have that thing we're trying to solve for, we'll push to the other side. So I'm going to subtract y over here. Okay, and then this, I'm going to subtract over here. Now what I can do is I want that y. So now every term has that y, I can factor that y out. Okay, now I'm in business. I'm going to divide both sides by x minus 1. So I get y is equal to, this cancels, negative 3x over x minus 1. By the way, that negative, you can leave it in the numerator. You can also bring it out front. It makes absolutely no difference to me. So our inverse function, negative 3x over x minus 1. Okay, so that's basically the algebra. Next we'll move on to the trig functions, which can be a little complicated. We will do some inverse trig functions with reciprocals, that's cosecant, secant, and cotangent, but for the most part my interest is with our three basic trig functions. So inverse sine, inverse cosine, inverse tangent. So the complication when it comes to the inverse trig functions is they're not one-to-one. So for instance, if we look at y equals sine x, so let's just look at it from pi to negative pi. That's going to be obviously enough to see that these are very much not one-to-one, right? So this looks like this. Right, okay. So what we see is it's not one-to-one here or here. It's repeating itself, and of course sine goes on from negative infinity to infinity just like this. So what we do with sine is we limit the domain to negative pi over 2 to pi over 2. So now we're just focusing in on that section, which then is one-to-one, okay? So that is going to be our inverse function. That's what we're going to focus on. So if I reflect that over the line y equals x, we get something that looks like this, and that would be y equals inverse sine or y equals arc sine of x. Those are interchangeable notation. This notation they're moving away from because here's the deal. Sometimes people see this and they go, oh, wait, that means 1 over sine. It does not mean 1 over sine. That is a sort of a weakness in that notation. We have to know in this context it means inverse function of sine. It does not mean the multiplicative inverse, the reciprocal. Okay, we have a name for that. We call it cosecant x. So we rely, when we talk about 1 over sine or 1 over cosine, we talk about those reciprocal trig functions. So we don't want to get them confused. All right, so sine, we limit to negative pi over 2 to pi over 2. Now what that means is that when we look for these values, our y values, by the way, this just means y is contained within, this is just some notation that you'll see me use, don't get confused by it. Negative pi over 2 to pi over 2. This ultimately we just end up memorizing, okay? So these are the outputs. That ends up being the range of inverse sine because it's the domain of sine. Okay, so let's move on. Y equals cosine. So once again, we'll look at it from negative pi to pi, and negative cosine, positive cosine looks like this from negative pi to pi. Okay, so once again, we see that it's breaking that rule that has to be 1-to-1 right there. It doesn't pass a horizontal line test. Okay, what we do with cosine, we can't limit it to negative pi over 2 to pi over 2 like we did with sine. We have to change that domain, and what we do is we look at it from 0 to pi, because now here what we're getting is 1-to-1. That part will pass a vertical line test, a horizontal line test. So this one ends up looking like, so that's our inverse function. Remember, I'm reflecting over the line y equals x. So y equals inverse cosine, or you can use the notation arc cosine is y goes from 0 to pi. Okay? Let's move up here for tangent, and then we'll move on to actually evaluating these things. So y equals tangent x from negative pi to pi. looks like this. So once again, we see that, and that continues on and on and on. So in this case, what we do is we focus in, once again, just like sine, on negative pi over 2 to pi over 2. Okay, except, here's the deal, this thing has a vertical asymptote at negative pi over 2 to pi over 2, so we leave that an open bracket there. Okay, so when we graph this, we end up with a horizontal asymptote. Okay, so y equals inverse tangent of x, or arctangent of x. Our range for that will be negative pi over 2 to pi over 2, not including those because our values don't exist there. All right, so let me write that up in kind of a simpler form, but just keep in mind what those things we end up focusing on. So in other words, in each one of these cases, we're limiting those domains. These are the limited domains that we agree upon. You do have to memorize those. Okay, so these are the most important elements of this. So our three inverse trig functions, and we have to remember are these limited domains. So, and I'm going to show you how do we calculate these. Inverse sine. So when we start talking about these, we'll use the unit circle, our standard unit circle. We're looking from negative pi over 2 to pi over 2. Okay. For inverse cosine, we're going from 0 to pi. And for inverse tangent, so it's the same as inverse sine, except we're not including the negative pi over 2 and the pi over 2. So by the way, and once again, the notation with any of these, we could also use the arc. And I believe on the AP tests they're moving towards the arc notation because then we don't have that ambiguous nature of thinking it means the reciprocal of tangent. Okay? So let's look at a couple examples here, and then that will be it. So examples. A, let's say I want to find arc cosine of radical 3 over 2. B, inverse sine, and I'm going to use these notations interchangeably. You should be comfortable with both. Inverse sine of negative 1/2. C, arc tangent of 1. And then D, inverse cosine of negative 1. Okay. So basically what we're doing is we're looking at when this is the output. So normally with cosine, we get a theta, and then on the unit circle, we give you the x of that value. So in this particular case, let's think of our unit circle here, okay? Now remember, we're only looking from here to here. Where is x radical 3 over 2? So it's right here. We know that pair would be radical 3 over 2, 1/2. We always use the y for the reference angle, which would be pi over 6. So that would be pi over 6. It's very important when you do your inverse trig, you only give one value. That is the most common error. People give multiple values. Keep in mind, if you're giving multiple values, you're basically breaking that it's an inverse function. You're giving multiple outputs, and therefore it fails the vertical line test. Excuse me, the horizontal line test. Inverse sine, okay. So inverse sine, we're talking from negative pi over 2 to pi over 2. Inverse sine, normally with sine, we get theta on the unit circle, and that spits out, theta, and that spits out y. So if our y is negative 1/2, we're down in this quadrant. So what I have here is radical 3 over 2, negative 1/2. Once again, it's the y that tells me the reference angle. The reference angle is pi over 6, but we're moving in that negative direction, so that's a negative pi over 6. Okay? Arc tangent. Arc tangent. Normally with tangent, we get theta on the unit circle, and we spit out the y over x. if I have a y over x equals 1, that means y and x are the same. When is y over x the same? When they are radical 2 over 2, radical 2 over 2. The reference angle there is pi over 4. And then finally, inverse cosine. Okay, so we're going from here to here. We have -1. So what that means is we're over here. And what's that value? It is pi. Okay. These do take a little bit of practice. You're really just reversing the trig values in what you do with the unit circle, but you just have to keep these domains in mind. So that's prerequisite section for inverse functions.